Hello and welcome everyone to part 4 of the course. In this part we are going to cover the parking smoke control systems, and I will try my best to include all the essential information that you need to know as a designer. That's why I'm going to include a very detailed parking classification, and I'm going to also mention the parking smoke control approaches, and after this I'm going to follow up with the types of the parking ventilation system and the parking smoke management system. After this, I'm going to focus on very important design notes that are related to the jet fan and the application of jet fan in the parking ventilation, especially on the smoke management. I have to be honest with you guys that jet fan information are very rare to be found anywhere. That's why this is one of the most valuable assets in this course, which is that I am covering the aspects of the design that are related to the jet fans and the application of jet fans in parking smoke management. After this, I'm going to talk about the makeup air and the introduction of makeup air into the parking during the smoke management mode, and I'm going to finalize this chapter by giving you a solved example on the smoke management calculation that are required to design the smoke management, and all of this will be in accordance to the related international codes and standards. So without further ado, let's dive right into it. One of the most basic information and knowledge that you need to be aware of as a design engineer is the very famous question of what are the types of parkings. Parkings are generally classified into open or closed parking enclosures, and this is not my classification. This is the classification of NFPA 101, which is the NFPA Life Safety Code. If we read the paragraphs on the right side of the screen, we will see that NFPA 101 is giving a detailed classification of the parking enclosures. If we refer to paragraph 3.3.284.8, we can see a definition of the parking structure. Parking structure is defined as a structure or a portion thereof used for the parking, storage, or both of motor vehicles. And if we refer to paragraph 3.3.284.8.3, we will find the definition of an enclosed parking structure or the closed parking structure, which is any parking structure that is not an open parking structure. And if you need to define the open parking structure, you need to refer to the following paragraph, which is paragraph 3.3.284.8.4. You will find that open parking structure is a parking structure that meets the requirement of 42.8.1.3. And if we refer to this paragraph I just mentioned the number of, which is the paragraph on the top right side of the screen, paragraph number 42.8.1.3, which is the definition of the open requirement for open parking structures. Open parking structures shall comply with 42.8.1.3 through 42.8.1.3.5. And these are the following paragraphs, and I'm going to read them for you, starting by paragraph number 42.8.1.3.1, which states that for natural ventilation purposes, the exterior sides of the structure shall have a uniformly distributed opening on two or more sides of the parking. The next paragraph, which is paragraph 42.8.1.3.2, it's stating that the area of such opening in the exterior walls on a level shall be not less than 20% of the total perimeter of the wall of each level. The next paragraph, which is paragraph number 42.8.1.3.3, it's stating that the aggregate length, which is the total width of the opening considered to be providing natural ventilation, shall be not less than 40% of the perimeter of the level. And this is quoted from NFPA 88, which is dedicated to the parking structures. The next paragraph, which is paragraph 42.8.1.3.4, it's stating that where the required opening are uniformly distributed over two opposing sides of the building, the above two paragraphs shall not apply. And the last paragraph on the bottom right side of the screen, which is paragraph number 42.8.1.3.5, it is stating that the interior wall lines and column lines shall be at least 20% open, with opening uniformly distributed to provide ventilation. And this is also quoted from NFPA 88A, which is related to the parking structures. And this is the official definition of the open parking enclosures, or this is the opening requirement that is usually required by the majority of the international codes and standards in order to classify the parking as open parking enclosure. And I did not summarize these requirements because I needed to state the exact requirement, because these are very important. In some scenarios they are required in some submissions. That's why you need to know the information from the source, which is the definition of the open parking requirement from one of its main sources. So what are the smoke management system approaches that we can use for the parking enclosure? Before I state this, I need to highlight that any ventilation system can be either a mechanical or a natural ventilation system. In order to use the natural ventilation, you need to follow the restrictions and the requirement which I have just stated regarding the minimum areas and locations of the openings and the sufficient opening area or percentage of the total wall area that need to be required and present in the walls of the parking in order to be able to classify the parking as open parking and in order to use the natural ventilation. However, if you are going to use the mechanical ventilation, whether if it is for a normal operation mode or the fire related operation mode, now in this scenario we need to understand and be familiarized with the smoke control approaches that are commonly used in the parking smoke control system. The first approach, which is the smoke management, and smoke management by definition in accordance with NFPA 92 is a system that is designed to maintain the tenable condition until the occupants safely evacuate the parking area, which means that the smoke management does not maintain the area of the parking free of smoke throughout the entire time of the fire, but it only maintains a safe conditions until the occupants evacuate the building or evacuate the parking floor safely. And this is the smoke management system. This is usually employed by the application of smoke extraction fans and maybe a natural ventilation as a makeup source through the ramps or openings, or a mechanical ventilation as a makeup source using supply air fans or makeup air fans. So it generally uses fans in the majority of the cases. These fans can be either ducted or can be non-ducted like the jet fans, as we will find out in the upcoming videos. And the second concept or the second design approach in the smoke management of the parking, which is the smoke containment. And smoke containment by definition in accordance with NFPA 92 is a smoke system or a smoke control system that actively contain the smoke spread within a certain amount of area or within a certain smoke zone, which means that this smoke containment system will actively control the spread of the smoke and will prevent the smoke from filling the parking, which means that if you are designing a smoke containment system for a parking of 40,000 square feet, this 40,000 of square feet will not be filled with smoke throughout the entire fire incidents or throughout the active ignition of the fire, which means that this smoke containment system will prevent the smoke from spreading horizontally throughout the entire area of the ceiling or the floor of the parking. And this is usually done by more than one means. But the main driving factor is the proper distribution of extraction points and the sufficient extraction and makeup airflow of the smoke containment system. And this can tell you that the smoke management extraction flow rate is usually much more less or lower in the quantity of the airflow than the smoke containment, which means that the smoke containment is much more expensive option, but it is a safer option, while the smoke management system is a much cheaper option. However, it is not the safest option available. And the third approach for the smoke control in the parking, which is the smoke clearance or the smoke purging. Smoke clearance or smoke purging is simply a mode that is usually activated after the fire is being extinguished, which means that after either the civil defense team or the firefighters have extinguished the fire, or after the fire protection system have extinguished the fire, then you have a residues of the smoke and the combustion products. You have the smoke which is partially or fully filling the place. So you need to get rid of this smoke in order to evaluate the damage of the fire and try to resume the normal operation of the application of the building, which is the parking. So you need to activate the smoke management system or the smoke containment system to suck the smoke out of the parking and to pump in or supply a fresh air to eliminate any presence of the smoke inside the parking. In other means, or in simpler terms, the smoke purging mode is the mode that is used to empty the parking from any smoke that is remaining after the fire has been extinguished. And in order to understand what are the exact requirements, you need always, when it comes to the parking smoke control approaches or the smoke control requirement, you need always to consult the local authority having jurisdiction or the local civil defense requirement. This is always step number one, because there is a relatively large variation between the local civil defense codes, and as we all know, the authority of the local codes supersedes the authority of the international codes. And this is a very important note that any designer should be aware of and should follow. Let us discuss each of the smoke control approaches for the parking system one by one, starting with the parking smoke management and the smoke purging modes. First of all, you need to understand that both of the smoke management and the smoke purging mode is usually built upon the sizing of the ventilation system based on the air change per hour, which means that you usually size the fan to have a certain amount of air change per hour, and this amount of air change per hour varies between 6 to 10 air change per hour. The majority of the designers consider 6 air change per hour during the normal operation mode, while they are considering 10 air change per hour during the fire mode. But this is not the most accurate method, and it sometimes causes or results in a great lack in the ability of the system to be able to control the smoke spread. Because the correct way to size the smoke system is not on the air change per hour, but on the actual fire load related to the actual car fire that will happen inside this parking. However, the most important information that you need to understand with regards to the smoke management mode is that it does not necessarily maintain a safe environment for the entire fire duration. It only is required to maintain a safe environment until the occupants complete the evacuation from the place. And some of these systems doesn't even achieve this control for this short amount of time, because they are poorly sized. However, you need to understand the difference between the smoke management and the smoke containment. So it needs to be clarified and stated clearly that the smoke management does not necessarily provide a safe environment for the occupants during the entire fire duration. And as we have mentioned, it is a common rule of thumb to consider a total extract flow rate equal to up to 3 to 6 air change per hour during the normal ventilation mode, and up to 10 air change per hour during the fire and the smoke purging mode. If we refer to the equation which is shown on the right side of the screen, we can see the equation of the air change per hour that we usually use in the sizing of the ventilation system based on the air change method, and it is shown in both the imperial methods and the metric units. The imperial unit is the equation on top, and it equals air change per hour equals 60 multiplied by the flow rate divided over the volume of the parking. And of course, you know the volume of the parking, and you can easily specify as a designer how many air change per hour you require. That's why you can get the Q or the flow rate easily. If you will use also the metric equation, you will find that the air change per hour equals 3.6 multiplied by the Q or the flow rate divided over the volume. And by knowing both the volume and the air change per hour, you can easily specify the flow rate that you need in both of the normal mode and the fire mode. Now let us talk about the parking smoke containment system design. And the containment, which is not the management, the containment system is the most accurate and the safest system when it comes to sizing the capacity of the smoke exhaust fan, because it is sized based on the amount of the actual smoke that is being generated from the actual fire scenario. And usually the smoke generated from the fire is much more than the value that it is calculated in the smoke management or by calculating the exhaust rate using the air change per hour. So the first thing that you need to know is that the exhaust flow rate is based on the actual fire size, which means that the exhaust flow rate will vary in the situation if a sedan fire is proposed, than if a truck is proposed, than if a hydraulic parking is proposed with multiple cars stacked above each other. It varies in accordance with the actual load of the actual fire and the actual amount of smoke being generated from the fire that might happen. You need also to understand that the exhaust flow rate of the fan should be minimum or at least more than the actual smoke produced. So when you do the calculation, as we will see in the example I will give in the end of this chapter, when you do the calculation, first of all you calculate the amount of smoke that will be generated from this fire, the actual amount of smoke. After this, you are going to assume a factor of safety, and then the total amount of flow rate of the actual smoke flow rate plus the factor of safety will equal to the exhaust fan flow rate. And this will lead to a fact that even if the parking is small, if you are trying to use a smoke containment system, you will have to apply relatively high exhaust flow rates. However, if the parking area is relatively large, then in some scenarios the smoke containment system, if you are going to use the fire load, this may result in a flow rate that is less than if you are going to use the air change per hour method, because the air change per hour depend on the volume mainly. So in case if the parking is relatively big, the volume as well will be big, which will reflect on the total amount of airflow required, that will also be big. That's why the smoke management system is not the most accurate system to predict the exhaust flow rate of the smoke management or the smoke control fan. You need also to understand that the smoke containment system usually have the higher cost or the highest cost, but it is as well, and as we have mentioned earlier, the most safe option that you will ever employ. And as a justification of the amount of the exhaust flow rate, which is relatively higher than the smoke management, you need to understand that the amount of smoke which is being generated from a car fire is usually relatively large. And this is due to the fact that the car is mostly made of plastics. And these plastics are very sooty and they produce a lot of smoke when they are on fire. And as we can see on the figure on the bottom right side of the screen, which is showing the plastics of the car in one word, you can see that in the modern cars around 50% of the car is plastic by volume and 10% is plastic by weight. And by 2020 the typical vehicle will contain 770 pounds of plastic material in comparison to 440 pounds in 2014, which means that there is relatively a large amount of plastic, and this amount of plastic is what is responsible for the production of the large amounts of smoke during the actual fire scenario. That's why the smoke containment system is requiring a relatively large amount of exhaust flow rate, because it is following the actual amount of smoke that it is being generated due to the fact that the car contains a relatively large amount of plastic in it. After we have discussed the approaches that are commonly followed in the design of the smoke control system for the parking, now let us discuss the type of the parking ventilation systems, how you will employ the system that will serve the purpose that you require. How will I design a system that will serve the purpose of smoke management or smoke containment or smoke purging? Usually the parking ventilation systems that are commonly used are either a ducted system or a ductless system. The ducted system employs a network of ducts that is distributed over the parking at high levels and at low levels to provide a uniform suction of pollutants and to provide a proper distribution of the exhaust ducting from the parking. And usually in this ducted scenario, you will find a duct running around the entire parking slots of the parking, because it depends on the local extraction from above where the cars are located. So this ducted system, we can see it on the top right side of the screen. This is a simplified illustration for the ducted smoke or the ducted parking ventilation system. You will find a network of ducts where the main branches will be running at high level and there will be a smoke extraction grills at high level, and you will see a small branches that are vertically dropping from the horizontal ceiling mounted branches. They are dropping to a low level to suck the pollutants of the cars when they are idling or moving within the parking during the normal operation. This is also depending on the local extraction of pollutants, especially from the exhaust pipe of the car during the normal operation. And this ducted ventilation system usually designed as follow, and this is a common rule of thumb if you are designing a smoke management system for the parking. During the normal mode, you will size the fans based on the fact that you need 3 up to 6 air change per hour during the normal operation mode, and this amount of the flow will be the total flow requirement for the extract fan. And you need also to understand that the parking is usually negatively pressurized, and it is negatively pressurized by approximate value of 85 up to 90%, which means that the extract will be more than the supply with this ratio, or which means that the supply will be 85% up to 90% of the extract value, so the supply will be less than the extract, and this will cause the parking to be negatively pressurized, which will prevent the exfiltration, or which will prevent the travel of pollutants or smoke from the parking to the adjacent areas. So this parking or the ducted system in the design of the parking ventilation system is designed in the normal mode based on the air change of 3 up to 6. 30% of the total amount of this flow will be distributed to be at low level, and 70% of this flow will be at high level, which means that the grills which you see on the high level will be sized and selected based on the fact that they need to extract 70% of the flow, while the grills at low level will be required to extract only 30% of the flow. And the activation of the ventilation fans will be triggered by CO sensors, or carbon monoxide sensors. Why carbon monoxide? Because carbon monoxide is a poisonous gas, and if it accumulated inside the parking, it can cause serious health damage. That's why we distribute CO or carbon monoxide sensors all around the parking, and the approximate area that is used for distributing the sensors is that each sensor will require a 400 square meter of area approximately. However, during the fire mode, the fans is activated at the high speed, which is sized based on 10 air change per hour. So it's more than 1.5 the capacity of the fan during the normal mode. And also you need to understand that you need to maintain the smoke at the highest level possible. You need to prevent the smoke from descending to low level. Otherwise, the smoke will cause asphyxiation to the occupants, and it will prevent the occupants from evacuating safely. That is why it is very important that the grills at the low level to have motorized dampers that automatically close this low level branch in the event of fire detection. Because if this low level branch is active during a fire scenario, it will suck the smoke from both low level and high level. And what will happen if you suck the smoke which is at high level from a low level? You will force the smoke to drop down and descend to be sucked from the low level. And by doing this, you will achieve the opposite of what is the purpose of the system. Because the purpose of the system is to maintain a safe environment for occupants to evacuate. However, if you force the smoke to descend to be sucked from the low level, you are now doing the exact opposite of being a safe environment. You are now exposing intentionally the occupants to smoke at low levels. That's why it is very important that the low level duct to have a motorized damper that closes during the event of a fire. And also you need to cross check the requirement of the authority having jurisdictions or the local civil defense with regards to the distribution of the ducted system. Now this is the first system, which is to have a network of duct that is being distributed all over the parking to suck the smoke evenly from the areas where the parking slots are there. But this is a ducted system. The second system, which is the ductless system, and ductless system is a system that simply have no ducts. In this system, we use what's known as jet fans. We can see a configuration for this system, a simplified configuration on the bottom right side of the screen. This figure represents that the parking is simply consisting, or the ventilation system of the parking, simply consisting of three main components. The first component, which is the fresh air or the supply air. The second component, which is the jet fans. The third component, which is the exhaust air. So the first component, which is the supply or the fresh air, this can be introduced by either fans or by ventilation shafts or by louvers. And the second component, which is the jet fan, and jet fans are simply axial fans that are used to push the smoke or push the air or push the pollutants from the source where they are generated to the nearest extraction points, which means that they are only responsible for pushing the smoke towards the exhaust point. So we are reaching to component number 3 of the ductless system, which is the exhaust point. Exhaust point is usually fitted with exhaust fans, and the exhaust fans are fire rated and smoke rated to maintain and withstand the hot smoke. So it's a very simple system, the ductless, and it is very cost efficient because there is no duct. And of course, having a duct running all over the place means that you will have coordination problems, you will have coordination clashes with a lot of services in the parking. And having a ductless system also have its limitations, because some authority having jurisdictions have certain restrictions or limitations on the application of jet fans, and some of them prohibit the usage of jet fans. That's why it is very important to cross-check with the local civil defense requirement and regulation. Okay, so now I have understood the two main parking ventilation systems, which are the ducted and the ductless. But I need to understand more about the pros and the cons of each of these systems. The pros and cons are represented in the variation of cost, the variation of the space available, the variation of the fan power, the coordination problems, and the efficiency problems. So let's make a quick comparison between the ducted and the ductless system. The ducted system have the main advantages of achieving a proper distribution and have the main advantage of local extraction points, which means that you catch the carbon monoxide or you catch the smoke very close to its origin. So you don't give it enough time to roam around inside the parking. You prevent the smoke from spreading inside the parking because you apply the concept of local extraction. While if we look at the ductless system, we will see that the ductless system generally pushes the smoke from the origin source or from the origin point up until it goes to the exhaust point. And in some cases it pushes the supply air to displace the smoke or displace the pollutants towards the exhaust point. So it doesn't necessarily suck the smoke, but it rather pushes the smoke towards the extraction point. And this is the main difference in the concept. But if we are going to compare from a cost point of view, we will notice that of course the ducted system have higher initial cost and higher operating cost. This is due to the fact that the duct and the material and the accessories that are used in the installation have higher initial cost, while the fans that are fitted to the duct have to overcome the pressure drop that is being generated from the air being pushed inside the air distribution network or the ducted network. That's why the external static pressure of the axial fans used in the ducted system are usually having a higher value and accordingly have a higher power than the jet fans. You need also to understand that jet fans does not consume a lot of power and does not require a lot of space. Actually, the diameter of the fan is very small and you doesn't have to require any distribution ducting unless it is decided by engineering analysis. However, from a space point of view, the jet fan will win this comparison because ducting require a lot of space. And of course, the space, the vertical space inside the parking is one of the major problems because you require a clear height of the parking that usually doesn't go below 2.4 meter. So you are very limited in height because you have also other services, including but not limited to the drainage piping, which are usually designed to have a gravity system, so it has slopes, so it is very difficult to maneuver around the drainage piping inside the parking. And if we are going to discuss the comparison from a fan power point of view, you need to understand that, of course, in the case of a ducted system, the fan power will be much more higher because the fan, as we said before, must overcome the pressure loss from the air being pushed inside the air ducting network. And from a coordination point of view, also the jet fans win because they does not require a lot of space coordination. However, you need to coordinate if you are employing jet fans that there are no obstructions mounted in front of the fan, because these obstructions waste the energy and the momentum of the primary jet that is being discharged from the fan. That's why it requires also a fair amount of coordination and a sensitive amount of coordination. And lastly, the efficiency. The efficiency of both of the systems can only be verified using a validation tool, including the CFD and the fire dynamic simulation. And I have prepared 3 amazing courses on this subject that help you validate any design of any parking system ventilation. These courses are available on Udemy. You can search by my name, or you can search on Pyrosim. You will find my courses available, and you can contact me for more discount or any clarifications. So let us summarize our discussion on the parking ventilation system using the ducted ventilation system. If we refer to the figure on the right side of the screen, we can see a representation for the typical mechanical ventilation that is used or done using a ducted smoke clearance system. And this image is taken from the British standard, and the reference number for the British standard is shown on the bottom right side of the screen. And in accordance with the British standard, 50% of the flow is required to be exhausted from low level, and 50% is required to be exhausted from high level. And the dark black rectangles are representing the extract grills locations. So, the ducted system in normal mode operation is usually sized based on the fact that you need to achieve 3 to 6 air change per hour. And the activation is done using CO sensors to activate the fans on and off during the normal mode. Whereas you need to exhaust from 30% up to 50% from the low level, and from 50% up to 70% at high level, depending on the local or international regulations that you are following. While during the fire mode, the minimum amount of air change that is allowed by majority of the local codes and standards and regulation of civil defenses is 10 air change per hour, and 100% of the flow to be extracted from high level. And this also requires careful ducting distribution and careful duct sizing to accommodate the fan and the amount of high flow rate that is run by the fan at high speed. Because if you do not account for the high speed in the running during the fire mode, you may subject the fan to static pressure values that are too extreme for the fan to withstand, and you may burn the motor of the fan if you did not take into account the amount of flow during the high speed mode or during the fire mode. That's why a careful duct distribution and sizing is required. You also need to cross-check before you start the sizing what is the vertical clearance available for your ducting network. That's why the coordination is very critical in this ducted ventilation system. We need also to highlight that this system is relatively more expensive than when you are using the ductless or the jet fan based system. And the importance of coordination in the ducted system represents the need to avoid conflicts with civil and MEP related elements. Civil elements like the beams and the columns, and MEP related elements like the cable trays and the mechanical service pipes and ducting and plumbing fixtures. You need also to provide a proper flow path and distribution, which means that you need to provide extraction or exhaust point at low level and at high level at the location of the car parking slots, and you need also to achieve a proper distribution to prevent any accumulation of smoke or pollutants like the carbon monoxide. And here are some notes with regards to the low level and high level exhaust. We need to clarify that the low level is not recommended during the active fire scenario because it forces the smoke to descend into low levels, and this will be harmful to the occupants and will cause the visibility reduction. In some scenarios, it will be so extreme that the occupants will not be able to escape the space safely. That is why it is very important to prevent or minimize the low-level extraction during fire mode. You need also to know that the low-level extraction, although it is not required in fire mode, but it is very important during the normal mode. And this is due to the fact that the exhaust fumes coming from the cars are having a high percentage of toxic gases, as well as some of these gases have higher density than air, so they accumulate at low level. That's why it is important to provide local extraction points at the parking slots at low level as well as at high level during the normal mode. But during the purging mode, since the place is already unoccupied and since it is already filled with smoke, there will be no objection to use the suction from the low level and the high level. However, during the evacuation, it is very risky and very dangerous to use the exhaust point from low level. Now let us talk a little bit more than the parking ventilation system using a ductless system or using a jet fan. The jet fan in theory is utilized in order to push the air from the fresh air point up to the exhaust point, which means that you are constantly providing fresh air supply into the parking and constantly pushing the pollutants and the smoke from the origin of generation to the nearest exhaust point. And you can see an illustration for the concept of operation at the figure on the right side of the screen, at the top right side of the screen. You can see that there is a fire in one of the cars inside a closed parking, and the inlet air or the makeup or the fresh air is being introduced from the right side of the screen, and there is a jet fan that it is mounted at high level at the ceiling, and the jet fan is taking the fresh air, increasing its momentum and discharging it in the form of high momentum, a primary jet flow that is pushing the smoke. And by pushing the smoke, you are achieving two purposes. The first purpose, which is to push the smoke towards the exhaust point, and the second purpose, which is you are limiting the spread of smoke, or you are controlling the smoke and preventing it from spreading further deeper in the parking. As we can see, the dark area, which is representing the ceiling jet of the smoke, this ceiling jet is usually spreading horizontally with a relatively high velocity. That's why you need to employ jet fans that discharge air with high momentum and high velocity to counteract the movement and the spread of the smoke and to maintain a limited smoke spread within the parking. So we can see from this figure a clear representation for the purpose of operation for the jet fan, but I still cannot visualize the jet fan as a designer. In this case, I will tell you, refer to the two figures on the bottom side of the screen. Jet fans are usually axial fans, and the most commonly known form of jet fan, which is the one at the bottom right side of the screen, which is an axial fan, a tube axial fan that have two silencers, one before the axial fan and one after the axial fan. These silencers have two purposes. One of these purposes is to dampen the noise that is being generated from the fan, and the second purpose, which is to provide a uniform distribution of the air before and after the fan to maintain the energy and the momentum of the primary jet. They are more like a guidance for the flow movement. You can see also that on the discharge side of the fan, which is the left side of the fan, there is what's known as guide vanes or jet fan deflectors, and these are used to guide the discharge if you would like to discharge the flow from the fan at a certain amount of degree, if you would like it to discharge it tilted and not horizontal from the fan. And this is very useful in the event of controlling the movement of the air and preventing it from hitting any civil obstructions like the beams and columns, because some of the drop beams have relatively high depth which can obstruct the discharge of the fan, and this is one of the solutions that you use to overcome this problem. And the second type of this fan, which is the impulse fan that you can see on the left side of the screen. This fan takes the suction from the bottom side of the fan, at which we can see a net or a mesh is mounted on the suction of the fan from the bottom side, and discharge it from the left side of the fan, which is a narrow rectangular nozzle. This nozzle discharges the air in two forms. The first form is, since the area of the discharge is smaller than the suction, it have a relatively high velocity. And the second form is that the discharge is at a certain angle downwards, which means that this is equipped automatically to discharge the air at an angle, which will give it an inherent ability to overcome the structural obstructions like beams, which means that this will be a very good option if there is high depth drop beams inside the basement ceiling. Moreover to this, I need to state also that the impulse fan, which is shown on the bottom left side of the screen, have a higher throw more than the normal jet fan, which is shown on the bottom right side of the screen, which means that this impulse fan, which is at the bottom left side of the screen, can throw the air at higher speeds and for more distances more than the normal discharge axial fan. When it comes to the design of a ventilation system or a smoke management system using jet fans, there is little to no information that can be found available. In this video, we are going to discuss some of the most important design notes when it comes to using jet fans in the ventilation or smoke management system. First of all, let's start with the factors that you should consider when you choose a jet fan. You need to know that jet fans are distributed across the area that is going to be ventilated depending on the area of coverage and depending on the spacing between the fans and depending on the thrust. So each of the jet fans that are available commercially, I'm not talking about the special applications. The commercially available jet fans are usually covering an average area of approximately 400 square meter. It can be more or less depending on the thrust. So based on this coverage area, you need to understand that there is a longitudinal spacing between each two fans and a lateral spacing between each two fans. The longitudinal spacing of each of these two fans, there is a general and common rule of thumb, which is to use 2/3 of the effective throw that you will find in the selection sheet of the supplier based on the thrust you've chosen, which is translated usually to 20 up to 30 meter for the majority of the fans. So this means that each two fans will be longitudinally separated by 20 up to 30 meters. The exact value shall be verified by using CFD analysis. While the lateral spacing of each two fans is usually ranging between 10 up to 15 meters, which means that you will put the separation distance between each two fans of approximately 10 to 15 meters. Okay. So this also leads us to a very important information. Based on what did you mention these spacing values? I will tell you. Usually the jet fan is used based on something that's called the primary jet velocity. And primary jet, which is the jet that is being discharged from the discharge side of the fan. This primary jet at the discharge point from the fan, it have high velocity. And as it keeps going inside the area that you are ventilating, this high momentum, high velocity discharge air loses energy. So this primary jet velocity drops down with distance, which means that the more distance the air will travel, the lower the speed of the air will become, until it reaches a certain degree where it is no longer useful and it is no longer achieving the required criteria. So this velocity or this point is called the primary jet termination velocity. And the primary jet termination velocity should never drop down below 0.5 meter per second or 100 feet per minute. That's why the suggested spacing, the longitudinal spacing and the lateral spacing is formulated in order to maintain the primary jet velocity above 0.5 meter per second. And this is one of the most important factors that you should check once you do a CFD analysis. So I gave you a range of the spacing, a longitudinal range and a lateral range. This range you should verify exactly if it's valid or no based on the results of the velocity distribution. It should always maintain a primary jet velocity above 0.5 meter per second. You need also to understand that you need as much as possible to avoid any circulation from happening and to avoid the presence of any stagnant areas, which means that you will distribute the fans evenly to ensure that there is no stagnant area that is having a low velocity or no velocity at all, because this stagnant area will be a source of problem if a fire happened or if any pollutant accumulated. You need also to understand that avoiding the circulations is usually done by the proper distribution of the fans, especially at sharp angles or bendings, and especially also from the structural elements like the beams. There is a very famous phenomena that is related to the jet fan's operation, which is the entrainment effect. Entrainment effect is simply meant that the jet fan is not only discharging air, but it is also pushing the air around the primary jet, which means that if you put two fans, the two fans will discharge air, but they will also induce or add momentum to the air around these two jets, which means that the overall flow is being discharged from the cross section of the area where the two fans is installed will be increased because of the entrainment effect, because the fans are not only discharging primary jet, but they are also moving the air around them, so the total airflow will be called the entrainment air. Also, you need to understand the activation and the control sequencing of the jet fans, because the jet fans are not always on and they are activated based on a specific control sequencing I will explain in the coming videos. Moreover to this, you need to understand that jet fans and the structural beams or columns are enemies, which means that whenever there is a beam or a structural element in front of a jet fan, it will cause a very high loss in the momentum and in the energy and in the velocity of the primary jet, because it will be like an obstruction in the face of the fan. It will turn this high momentum into circulations and it will not allow the air to move with high speed as intended. That's why you should be very careful with the structural elements inside the place that you are trying to put jet fans inside. And there are two solutions to overcome this problem of the drop beams or the obstructions, especially the structural obstructions. The first one, which is to use deflectors. The second one, which is to use the induction fan or the centrifugal jet fan. Also, you need to understand that you are not only caring about the jet fan inside the area. Let's say if this is the parking, you're not caring only about the jet fan and the exhaust fans, but you need also to care about the makeup air velocity. The makeup air velocity should not be high, because if it is high, it will cause circulations, and these circulations will act like mixers. They will mix the fresh air with the smoke or pollutants. That is why it is almost mandatory that the makeup air velocities to be relatively low, in order to maintain a free, fresh stream of the makeup air without any circulations or mixing of the pollutants or smoke in the event of a fire. Lastly, you need to understand that the height difference of the area which you are willing to ventilate using jet fans is making a great difference on the performance of the fan, which means that if you use the same jet fan in an area that have a clear height of 3 meters, it will not be the same as if you are using the jet fan in an area of a clear height of 2 meters, and it will not be the same if you are using the jet fan in a space that have a clear height of 4 meters. Of course, the throw value will be different, and this is related to the losses in the primary jet and in the momentum of the primary jet. Think of this place as a cross section as if it was a duct, and this jet fan is like a fan pushing the air through this duct. If this duct got bigger, if the height got bigger, the throw will be affected, and if it got smaller height, the throw also will be affected. And these are one of the major key components that you use as a designer when it comes to designing a ventilation or a smoke management using jet fans. If we refer to this figure on the middle of the screen, we can see a graph from the famous fan manufacturer Flacked-Woods, and this figure gives you the approximate coverage area of the fan for each type of the models that are commonly manufactured. You can see on the horizontal axis the models, and below each of these models a table. This table gives you two values. These values are the coverage area of each model of these fans, and you can notice two colors. The cyan color or the light color is the velocity of the fan or the coverage area of the fan in the normal or the low speed mode, while the dark blue color is the coverage area of the fan in the high speed mode. And you can see an illustration of the photo for each model, and it will show you or help you illustrate the difference between each of these models. You will notice, the first thing you will notice is that the smallest in diameter are located on the right side of the screen, and the highest in diameter are located on the left. You will see also that the centrifugal fans have the highest coverage area of all the jet fans, and this is a very known and a very common advantage of using these fans. You will see also that the average coverage area in normal mode for the jet fans ranges, of course this is during the low speed mode, ranges between 120 up to 600 square meter. And from this we formulated the average coverage area of the 400 square meter in the previous video. You will notice also that on the fire mode the coverage area almost doubles because the flow and the speed almost doubles as well, and it ranges also on the same range of 250 up to 600 square meter of coverage area. The only exception for this is the induction centrifugal fans on the left side of the screen. They have almost double the coverage area of the normal fans, and this shall give you an indication of the variation of the coverage area of the majority of the commercially available jet fans. However, in this figure you can see a figure showing the recommended longitudinal spaces in meter by the same fan manufacturers, which is Flactode, and this is based on a typical 3 meter high car park. These are the same models, and the table below each model represent the high speed longitudinal spacing in dark blue and the low speed or half speed in light blue or in cyan color. You can see that the throw of each fan can reach in the normal mode starting from 20 meter up to 70 meter, while in the fire mode it can reach from 40 or 50 meter up to 85 or 100 meter. And this value is the ideal value without the presence of any obstructions or any losses in the momentum or any losses. That's why the recommended value is based on using 2/3 of this ideal speed value and the ideal distancing value, which means that if you are selected a fan based on a throw of 30 meter, you should use 2/3 of this value as the actual longitudinal spacing of this fan, which means that 2/3 of 30 meter will be 20 meter. So you should distribute your fan based on this actual value, which is 2/3 of the throw you will find in the manufacturer's catalog. And by doing so, you will ensure that the primary jet velocity will not drop below 0.5 meter per second. And in this video we can see the recommended lateral spacing in meters by the same fan manufacturer, which is Flactode, based on some of the commonly available commercial models, and these are the same models, and the table below represents the lateral spacing in meters in both high speed mode and half speed mode, or high speed mode and low speed mode. The high speed mode, you can find that the average lateral distancing of the fan starts from 5 meter and reaches up to 20 meter, while in the normal mode you will find it starting from 5 meter up to 10 meter, and it can vary slightly from supplier to supplier or manufacturer to manufacturer, but from this you can get a sense of the average value that is available for the most or the majority of the commercial models of the fan. But the reference for this should be the supplier's manufacturer catalog. And you should not increase the lateral distancing, because if you increase the lateral distancing, you will increase the induced air and the amount of the total entrained air, and this will negatively impact the exhaust fan, the axial exhaust fan. This means that the axial exhaust fan, if it had a large entrainment air, it will need to be more or bigger size to be able to suck the increased amount of air that is coming as a result of the increased entrainment air. That's why you should stick to the values of the longitudinal and lateral spacing that are related to the supplier, and if they are not available, use the rule of thumb which we have explained above. And you need also to understand that the CFD analysis is the main criteria that defines the performance of the fan and the validity of the spacing that you are using. What you are seeing right now on the screen is the velocity distribution of a jet fan CFD analysis, or simulation results for the velocity from a jet fan. We can see the scales. There is two graphs. One graph from a top view, which is a graph on the top of the screen, and one graph as a sectional view or a side view, which is a graph on the bottom of the screen. You can see the scales for the velocity values or magnitudes. As we all know, the red indicates high velocity and the blue indicates low velocity. So we can see that the ambient is in blue. This is because the ambient have relatively low velocity or no velocity with respect to the fan. And we can see also there is vertical scales for the distance from the fan until the end of the velocity of the fan. We can see that the jet or the primary jet coming from the discharge from the fan, from the plan view and the section view, have a red color, which means that this is the highest velocity area. Afterwards it tends to be in yellow, and then green, and then in light blue, and then in blue. This shows you the indication of the decay of the momentum and velocity from the primary jet from the jet fan. As we can see on the scale of the distance or the meters, from 0 up to 15 meters from the fan, the velocity is mainly in red and yellow, and these are the highest value of the discharge or the throw and the velocity of the jet fan. After this, it will become green from 15 meter up to 30 meter. After this, it will start to go in the blue region, and this indicates that the velocity will start to decay after 30 meters and up to 80 meters. We can see a highlight in red with regards to the blue area, and this indicates the decay or the end of the primary jet. It is highlighted on the scales, the horizontal and the vertical scales, and this will help you see where the primary jet terminates, and accordingly you can select the effective throw of the model of the jet fan you choose. And from here you can see the termination velocity effect of the fan. That's why the CFD is extremely important, because it will help you define the exact effective primary jet termination velocity according to your scenario, because in one scenario maybe the parking height is 3 meter, in another it will be 3.5, in another it will be 2.4 or 2.8. So the throw values, the theoretical ones in the catalog, should not be used. That's why you should follow the 2/3 of this effective throw, and also you should support your design with a validation using the CFD analysis for the jet fans. And as I have mentioned before, I have prepared 3 magnificent courses which are covering in full detail the steps and the details of the CFD analysis and how to analyze the results and how to understand the physics beyond it. So check them out on Udemy. If we remember, I have stated in earlier videos that the enemy number 1 of the jet fan installation is the beams or the drop beams or the structural obstructions. So on the figure on the top left side of the screen, we can see that when the fan is installed in the face of a drop beam, it will affect the flow, and the primary jet will have a very or a relatively high loss in momentum and in velocity and in energy of the air because of the obstruction that is up ahead the fan. And I have mentioned as well that there are 2 options to solve this problem. The first option, which is to install a deflector on the discharge side from the jet fan. If we refer to the figure on the top left side of the screen, we can see the deflector mounted on the discharge of the jet fan. And the deflector is simply like a louver, but you have the liberty to move around these louvers with a certain angle to tilt the discharge a little bit down. And when you tilt the discharge down, you can overcome the losses that are caused by the beam, because the main primary jet is not hitting the beam anymore. However, it's tilted a little bit down. So this means that the highest velocity of the air will be discharged downward with a certain angle tilted from the horizontal axis, and this can be shown on the figure on the bottom side of the screen. We can see the red is indicating the high velocity regions, and the green indicates the extension of the primary jet from the fan, which is tilted downward. So this is an accessory to the fan. You need to check it with the supplier, but this is one of the easiest solutions to overcome the drop beams, and drop beams are a fact that exist in 90% of any basement that you will work on. That's why it's very important to cross-check the drop beams levels and if they exist or no. If we refer to the figure on the left side of the screen, we can see the discharge from a jet fan, which is relatively located on the right side, and we can see also 2 drop beams. And on the scenario on the left side of the screen, the discharge from the jet fan is horizontal and it is hitting the beam. That's why we can see in the red the primary jet, and we can see the green and blue regions are the regions that are stagnant or have a relatively low velocity. We can see that after the air is hitting the drop beam, it is causing circulations to happen and it is losing momentum, and the throw is not effectively pushing the air after the fan and especially after the drop beam, which means that the drop beam represents a high loss to the momentum and the velocity of the discharged air from the jet fan side. However, if we apply the solution which we just spoke about, which is the jet fan deflectors, we can see the difference in the result on the figure on the right side of the screen. As we can see, after tilting the flow downward by installing the deflectors, we can see that the majority of the flow after the fan is represented in red, which indicates that the momentum is 100% intact and there is no loss or reduction in the momentum or the velocity of the fan, because the air is flowing below the drop beam and it's not hitting the drop beam. Thus, it is maintaining its momentum and velocity. Also, there is a very important note to be followed, that it is highly recommended to install the jet fan parallel to the beams as much as possible, not perpendicular. But if there is no other way but to install it perpendicular, then you need to consider to install a deflector on the discharge side of the jet fan, and you need the exact right angle that will prevent any circulation related loss. Following up on the entrainment effect, here is an elaboration of the effect related to the entrainment of installing multiple jet fans in parallel. If we refer to the figure on the right side of the screen, we can see 3 jet fans installed side by side in a confined space, and this confined space can represent a parking or any other enclosure. So we can see the color in red represents the primary jet of the fan. We can see the colors in blue representing the air in the parking or in the enclosure, and the air in blue have relatively little to no velocity. However, between each primary jet we can see a green and a yellow area. This green and yellow area is the air that is surrounding the primary jet, and although there is no jet fan in this area, but the air have high velocity relative to the other stagnant air. And this is due to the entrainment, because the primary jet have high momentum, so it is transferring this momentum to the surrounding air, which leads to an overall increase in the velocity of the air surrounding the primary jet. That's why the area surrounding the 3 primary jets have green color, which means that this area have relatively high velocity. Of course, it is not as high as the red color of the primary jet, but still it's a higher velocity than the remaining of the enclosure, which means that if you need to install an exhaust fan to suck the air from this enclosed space at the end of it, you need to account also for the entrained air. And this can lead to sometimes that the total flow of the axial exhaust fan is doubling, and it can reach sometimes from 4 to 6 times double the flow of each of the jet fans. And this is due to the explanation I've just said, that the primary jet gives momentum to the surrounding air and it's increasing its velocity as well. So in case of a fire, in order to prevent the accumulation of the entrained air, you need to account for the entrainment effect and its effect on the sizing of the axial fan at the end of the parking. And sometimes, in some rare occasions, if the entrainment effect is not considered, the total flow of the axial fans can be up to 9 times in case of the induction fans, which can have a huge impact on the sizing of the axial fans. So this needs to be evaluated carefully in the case of the axial fan and the normal jet fan, and also the induction or the centrifugal jet fan, which means that in order to account for the axial fan extract flow rate, you need to sum the flow rate of the jet fan plus the entrainment effect related flow. This leads us to a very important note, that the effect of the lateral spacing between each jet fan can have a huge impact on the entrainment effect, which means that if you increase the spacing between the jet fans, this will give you more entrainment effect, which means there is more induced flow from the momentum transfer from the primary jet to the surrounding air between each 2 primary jets. And we can see the difference here between the figure on the left side of the screen and the figure on the right side of the screen. The figure on the left side of the screen represents a proper sizing or a proper spacing between each lateral jet fan distancing, and this is causing minimal to very small entrainment effect. As we can see, the majority of the flow is actually the flow of the discharge of the primary jet. There is very small entrainment related airflow. However, on the figure on the right side of the screen, if we increase the lateral spacing between the jet fans, you will notice that the overall resultant flow rate will be the primary jet of the 3 fans plus the green flow rate, which is the entrainment flow between the 3 primary jets, which means that you have more flow that you need to suck away from this enclosure, and this shows you clearly the effect of the entrainment on the sizing of the axial fan. Now let us discuss the jet fan control sequencing during both the normal operation, which is the pollutant operation, which is the operation for the purpose of heat removal or carbon monoxide removal or whatever purpose the fan is installed to during the normal operation. Once you have specified the sizing of the fan, the selection of the model, the spacing of the fan, then you need to define the control sequence. And control sequence in the jet fans installation is relatively straightforward. This paragraph is quoted from Ashri in the chapter related to the design of the enclosed vehicular facilities, especially on the parking area. So as we can see, the following sequence, and I'm reading from this paragraph, the following sequence is an example for the normal ventilation and the demand-based sequence. This example measures the CO concentrations, but for other contaminants, it should be calculated and evaluated accordingly. It's shown here that there are 5 modes of operation. Of course, when you install a jet fan during the normal pollutants mode, you also install a carbon monoxide sensor. And this sensor gives the activation signal on or off to the jet fan. Accordingly, the fan will be activated or deactivated. So, based on the signal of this carbon monoxide concentration sensor, the fan will receive the command that you want it to do. So here you can find at each concentration the signal that is related to this concentration. So in case if there is 0 ppm, which is 0 particle per million, or 0 concentration of carbon monoxide, the action requested will be only supply and the exhaust fans, which are the axial fans that are installed to supply the fresh air and extract the air from the parking, if required, in order to maintain the minimal air change. However, if the carbon monoxide concentration is more than 15 ppm or particle per million, then both the supply and the exhaust fan, the axial ones, will be on. However, if the carbon monoxide ppm or concentration is between 15 and 35 ppm, some of the jet fans will be activated, and this will be based on the zoning and the arrangement of the jet fan, if the parking area is small or relatively of big area. However, if the carbon monoxide concentration increased more than 35 ppm, then all of the jet fans will receive a signal to be activated. However, if the carbon monoxide concentration from the CO sensor increased to a value above 100 ppm, then all the fans will be activated on the high speed or on the fire related speed. All the fans, I mean all the axial fans and all the jet fans. This is a simple control sequencing that is followed by the majority of the operation scenarios. However, in order to specify the exact sequencing required, because some of the international codes and standards have a variable allowable limit for the carbon monoxide. So you should refer to the authority having jurisdiction, regulations, and to the related international codes and standards that you follow. The British, the American, the Australian, some of these codes are a little bit slightly different than each other. When it comes to the operation of the jet fan during the emergency or the fire mode, here is an example which is quoted from Ashri as well, showing the sequence in case of a fire. And I'm reading the paragraph. The first action we'll be taking is that the heat or the smoke sensor will trigger. The second action is the waiting period. And the waiting period means that the fan will not activate instantly. And this have a very good reason I will explain in the following paragraph. The waiting period is required in order to confirm if the sensor is faulty or if there is an actual fire scenario. The third action, which is the fire alarm, goes off. The fourth action is to turn on the supply and the exhaust fan on the fire related floor in order to maintain a negative pressure, and you should close the exhaust damper on the non-fire floors if local codes allow the ventilation system operation during a fire event. And action number 5, which is to wait an evacuation delay period. Action number 6, which is to turn on all jet fan at full speed. Action number 7 is to run the system until the fire department turns it off. So the reason for the delay period is from the next paragraph, which is on the right side of the screen, stating that the jet fan are not turned on immediately, and this is because the smoke had not had sufficient time to accumulate and cause harm to the occupants. Turning on the fan immediately may unnecessarily spread the smoke. For example of this, the British standard number 7346-7 recommends a waiting period, with the length based or determined based on the building type, building size, and number and type of occupants. Also, we need to understand that the above operation may require a control panel for the fire department to allow for individual fan control. Now let us talk a little bit about the makeup air for the parking smoke control systems. You need to understand that the makeup air can be provided by more than one way. The first way, which is to use a ducted distribution makeup air network, and this is usually introduced via an axial fan that is connected to a ducting network that supplies fresh air with a specific velocity at a relatively low level, because you do not want to disturb the smoke layer and the smoke accumulation, because you need to maintain a smoke-free area at the low level, and this is the second reason to supply the fresh air from low level. And the second method to provide the fresh air, which is to provide it by using ductless opening, or a makeup air well or a makeup air shaft with a motorized damper to turn on and off as requested with the related system. The third option, or the third mechanism to provide the makeup air, is from the ramps that are connected to the same smoke zone that you are working on. And especially when it comes to the ramp usage or utilization as a makeup source, you should check the local civil defense regulations and limitations, because some local defense regulations prohibit to use the ramp after a certain area, which means that this local regulation will tell you that you are allowed to use the ramp as a makeup source for the ramp as long as the parking area does not exceed this specific area. That's why you should consult the local civil defense regulations, because if your parking zone exceeds this area, then you are not allowed to use the ramp as the primary source. You need to add also another source, which can be one of the two above sources. You need also to understand that the fresh air and the exhaust air locations should be on opposite sides, or optimized as much as possible to eliminate any short-circuiting of the air, which means that you need to run the fresh air inside the parking and distribute it evenly as much as possible, and avoid locating both the fresh air and the extract near to each other. Lastly, you need to understand that the makeup air velocity should be cross-checked to prevent any adverse effects, meaning that if the velocity of the makeup air is relatively high, it will cause mixing the smoke with the fresh air, which will cause harmful effects, which in turn can lead to spreading the smoke intentionally rather than maintaining the fresh air area clear of smoke. Hello everyone, and welcome to this example on the sizing of the smoke heat venting system. In this example, I'm going to size the venting system for a warehouse, and the size of the warehouse I'm considering is 300 feet in length by 150 feet in width by 35 feet in height. So first of all, I'm going to start with the basic equation that is stated in International Building Code for sizing the area of the vent, which is stated here, and it equals the volume divided over 9,000, and the volume will be in cubic feet. So I'm simply going to start by calculating the vent area, which is the first step, and I will multiply the 300 by 150 by 35 and divide it over 9,000, and it will equal 175 square feet approximately, which is translated to 16.26 square meter of vent area for this warehouse area. After this, I'm going to consider that a factor of safety of 30% will be applied, so I'm going to multiply 130% multiplied by the 16.26, and it will give me a total area of 21.13 square meter, a total area of vent. So I will consider a 22 square meter of total vent area for this warehouse. After this, I'm going to assume that the smoke layer depth will be designed for a value of 20% of the warehouse height. So it will equal 20% multiplied by 35 feet, or 20% multiplied by 10.7 meter, and it will give me a design smoke layer depth of 2.14 meter. So this is a designed depth or allowable depth for the smoke layer. After this, I'm going to refer to paragraph 5.4.1.1 from NFPA 204, and I'm stating that this paragraph is stating that the area of the unit vent shall not exceed 2d square, where d is the design depth of the smoke layer. So I'm going to cross-check the maximum allowable vent area to make sure that I'm not exceeding the 2d square, where d is the depth of the smoke layer. This is just a cross check. So step number 4, I'm going to calculate the maximum allowable vent area, and it will equal 2 multiplied by the smoke layer depth square, which is 2 multiplied by 2.14 square, and it will give me 9.1 meter. square. So this is the maximum allowable area for the vent. So the single vent should not exceed under any circumstances 9.16 meter square. Now the next step would be to calculate the vent spacing and dimensions. So for the vent spacing and dimensions, I'm going to refer to the NFPA, which is stating that the maximum vent spacing should not exceed 4 and 4 is the 4 times the ceiling height. So I'm going to multiply 4 into 35 feet, or 4 multiplied by 10.7, and it will give me 42.8 meter. So this is the maximum distancing that the separation distance between each two vents should not exceed. And this is also a cross check. After this, I'm going to consider that the vent area will be a smaller value so that I can distribute the vents properly throughout the entire ceiling area. So I'm not going to use 1 or 2 big vents. No, I will use small vents, and I'm going to use one of the dimensions that are commonly found in the catalogs of the suppliers of the smoke heat vents. So I'm going to consider that the smoke vent will have a 2 square meter area, which is translated into 2 meter length by 1 meter width. So the new area of the vent will be 2 square meter. So this is the single vent area. So in order to know the number of vents, I will divide it over the total allowable vent area, which is 22 square meter, which we have calculated in step number 2. Thus 22 divided over 2, it will give me 11 vent. That's why I'm going to distribute the 11 vent equally and evenly throughout the entire ceiling area of the warehouse. To do this, I'm going to divide the length of the warehouse over the number of vents. They can be in single arrangement or in dual arrangement. Single means 1 vent, and dual means 2 vents side by side are distributed across the lateral dimension. However, I'm going to consider, of course it's up to the designer and it's up to the CFD analysis results. However, for simplification, I'm going to assume that I will use a single vent row. This means that I will divide the entire length of the warehouse, which is 300 feet or approximately 90 meter, over the new number of vents that I have calculated, which is 11 vent. This will give me that the separation distance between each vent of 2 square meter area will equal 8.1 meter, and this is calculated in step number 6. Lastly, step number 7, you need to verify your design using a CFD analysis or a fire dynamic simulation, and as usual, I need to remind you that I have prepared 3 magnificent courses handling this topic in special.